and thank you, Michael, and OSF and GitHub as well. So I'll just ask that people will keep their mics muted for the most part during the chat. Lisa did say that they don't mind any questions during the talk if you'd like them, but otherwise just put them in the chat and we'll have loads of time to get to them afterwards. So a quick little introduction for Lisa. So she is a professor of psychology at the University of Glasgow in the School of Psychology and Neuroscience, and a founding member and current associate director of the Psychological Science Accelerator, founder of ManyFaces, and I've actually shortened this, Lisa, because you've far too many achievements, and a member of the psyTeachR team for reproducible research educational resources. So in their talk today, they will summarize the benefits of using code to process and analyze data, give some practical tips for developing your skills, demonstrate how data simulation can improve your research, and discuss the benefits of code review. So over to you, Lisa.
All right. Thanks so much for inviting me. It's always really exciting to talk to people who aren't psychologists, although I don't know if any of you also identify as psychologists. I'll just get my screen shared a second here. Let's see if this works. All right. Can you guys see this on the screen?
All good.
Awesome. All right. And URL up here gives you all the slides. There's a link at the very end to the code that made all these slides, because I coded these slides, of course. How could I not for a talk on why code? So sometimes I go off on tangents. I'm going to try to kind of zoom through this so that we can chat about coding and what are your challenges in sports science. So you need to see the abstract. Why do we use code? Number one reason to learn how to code is you can make amazing plots. This is how I got into code. And I'll show you later a link to where you can see a tutorial paper that some colleagues here wrote, and I helped with as well, on how you get into R through graphics. So learning how to plot for people who don't use R. You won't be able to make plots like this right away, but the skills build up really fast. So these are some plots that I made for the 30-day chart challenge, which is running this month right now, but these are for last year's. They give you a kind of a remit every day, so a data set or a theme, and then people make charts of really varying levels. So you can make super cool charts. I'm going to show you a little bit of an example. There's going to be code here. If you're not a person who codes, don't worry about this. It's just kind of to give you an overview of what it might look like to be able to build up a chart with code. So we've got some population data from the UN, and it comes like this. You can do some code trickery to pop it into a format like this. So we've got sex, the year, age groups, the population of people, and the percentage of people in that population age group. And this is just for the year 2020. And we want to make a plot that looks good of this information. And thinking about, if you're not a person who codes, what would you do with this data? Pop into Excel. How would you make the chart? Here are some of the cool things that you can do with code. So we could just start out, ggplot is my favorite way to plot data. It's not the only way, but there's a lot of resources on it. And you just tell it, like, what do I want on the x-axis? I want to put age on the x-axis, percent on the y-axis, and we want fill, the sort of the color that fills whatever plot we're going to make, to be different for different sexes. And then we can say, what kind of visualization do we want for this plot? A column plot. So already filling in some colors for you. We can customize everything and flip the axes around, just one more line of code. You can go back and forth and see what you like. And center the columns. So basically here, I just made all the male data negative numbers and all the female data positive numbers, so they line up in the middle. And then we can fix the titles. It's just another quick line of code. Get rid of that legend. Customize the colors. The default colors work okay, but they're not great, and we could do better. Then we can customize the axis, so the axis makes a bit more sense. add some annotations, just a line of code saying what text do we want and where and what color should it be. And then we can animate it. So we've got data from every 5 years for a while. Just a few extra lines of code and you've got an animated plot. Like, the plots are so good when you learn coding methods for creating plots. So this plot took me about 3 hours to make. Like it's not a lot of code, but there's a lot of trial and error when you're first developing a plot that you haven't made before. But this plot took me 3 minutes to make after I'd done that. So that's another one of the big advantages to learning to code is reusability. If you're doing anything more than once, you might put a little bit more effort into it the first time around to do it in a code way rather than like a point and click way in Excel or other things that make plots. But once you've got that workflow down, if you need to adjust it for a slightly different data set or a slightly different visualization, maybe we don't want to look at male versus female, but at 2 other groups, it's just changing a few lines of code and you're done. I'm going to put my screen sharing thing. There we go. Okay, so reusability, a huge advantage for why we code. Oh, no, there we are. But another, probably more important even, reason to code is error detection. So Michelle Naughton and colleagues looked at 250,000 p-values with the StatCheck tool. If you don't know about StatCheck, I'd recommend looking at it, checking it out. It goes through papers and finds values for statistical tests, things like analyse t-tests, where you've reported, say, the t-value and the degrees of freedom and the p-value. And those 3 pieces of information have to be internally consistent. If you are as old as me or older, you may remember, I learned this as an undergrad. You did your t-test and you looked up the t-value, looked up the degrees of freedom in a table in a big book, and it would tell you what's the p-value for those 2 things. So StatCheck just checks, is the p-value the one that fits with that t or the f value and the degrees of freedom? And from 250,000 p-values in 8 major psych journals that they looked at, half the papers had at least 1 inconsistent p-value. These could be typos, these could be errors, these could be fraud. About an 1/8 of the papers, so a quarter of the ones that had inconsistent p-values, had errors that could affect the conclusions, change something from significant to not significant. Errors were more likely to be erroneously significant than not, which is not necessarily a sign of fraud. I think if you're expecting something to be significant or it's exciting that it is, you're not going to double check, did you make a mistake? But if you were expecting it to be significant and it isn't, you might double check and find your mistakes. So how does code fix this? This being able to code your analyses may not necessarily fix your fix things like typos or other errors, but they at the very least help us figure out where did those come from, makes the errors recoverable. And there are also techniques for taking the values from your analysis and directly putting them into a paragraph or into an entire paper and being able to compile the paper with insertion of your statistical values directly from the code, making it less likely that you'll, let's say you forgot to exclude yourself a trial run and you'd written up the paper with all the values, now you have to replace them all. It's really easy to forget to replace one. Whereas if you've done all of that with code, you're not going to forget to replace one. There's also computational reproducibility of results is greatly increased when you do your results with code rather than in a point and click interface where the exact steps that you took. I know like in SPSS, you can record syntax and you can write syntax, but a lot of people don't. And these steps are lost. And it's really shown up by things like this Hardwick paper where they found out of 35 articles in cognition that had data, they could only reproduce 11 of them independently, like without, so looking at the paper, looking at the data, they tried to reproduce all the results. 11 they succeeded, 11 they needed the original author's help say like, what exactly did you do here? It wasn't clear at all. And 13 of them, the original authors couldn't even figure out how to make all those numbers again, which as a researcher is just my nightmare and would be real embarrassing. But has already happened. I've started a project going through all of my old papers and writing the code for stuff that I published in like 2003 that didn't have code associated with it, but I've still got the data. And I found so far out of the first like 8, one number that I have no idea where it came from. I'm pretty sure it was a typo in the paper. So what if papers have code? So Obles and colleagues looked at 62 registered reports, 37 with analysis scripts. Only 31 of them did run, and 21 of those reproduced all the main results, which is like not perfect. And we're going to talk at the end of this talk about code check and how do we make that a little bit better. All right, so these reasons to do some coding, how do you develop the skills that you need to be able to code? Because it may not be something that you were taught as an undergrad or in your postgraduate education. A lot of us have had to develop these skills independently. So here are my top tips for learning to code if you either are not happy with your skills yet or just starting from scratch. So taking a workshop in your area. The first hour workshop I ever took was in biology, and I was trained in biology. I have a master's degree in biology. I love it. We did some interesting stats about squids in the class that I took, but it just wasn't directly related. It wasn't a type of analysis that I would do for my own work. And this is pre-tidyverse and pre-ggplot. So like the plots were ugly back then. And I just like didn't use R again for almost 8 years because it didn't seem connected to what I was doing. So if you have the ability to take a workshop in your area or with the type of analysis that you're interested in, I think that's the best way to get started. And the next two are basically the same tip, like embed R in what you're doing every day. Practice as regularly as you can, not just, and not R, like any coding language. You can use Python to code your analyses. Julia is really good. In psychology, R10 is the probably most common language, and I'm going to be kind of talking a lot about R resources, but most of what I'm talking about applies to any other coding language you would use to do analyses. But getting it into your daily practice and practicing as regularly as possible, and not just once a month pulling out your code and having a look at it. You'll forget what's going on. There are ways, like I use R just every day for everything. I use it to rename files and to move things around on my computer and to create websites and to create talks like this one. So the more you can do that, the more comfortable you'll get and the faster you'll get with other things. But also there is the do something fun. So this 30-day chart challenge is just finishing up. If you have a look at, let's see. Can you guys still see this? Yeah. All right. So 30-day chart challenge here. It's going to the Twitter one, but they seem to right now be doing something about Bigfoot. People are all making maps about Bigfoot, which is very cool. We'll go back in here, full screen that. There's also Tidy Tuesdays. So R for Data Science is an organization that puts on kind of our learning events. And every Tuesday they release a data set. They do a short, like 5-minute podcast about the data set. And then people post their plots on social media. And it's a great way just to like get some interesting information and see what other people are doing. Some of the plots are really, really simple, or sometimes people do things like tables or data manipulation. And then tables also are another cool way to present your data. And there's a table contest that runs every year. And this was my favorite one from last year. It won the competition for tutorials. So if you click on this, I'm not going to click on it now, but if you come to this talk and click on that, you'll go to their tutorial, which shows you step-by-step how to go from the raw data for their Tour de France data set to a plot that looks like this with like little flags and t-shirts, and it's just really cool. All right. I would be remiss if I didn't put a plug in for the psyTeachR group, which is a group that I'm a member of here at Glasgow. We create open resources for teaching reproducible research. So the R stands for reproducible research, not necessarily for R stats, although we do use R stats. And there's linked to that paper I was talking about, the data visualization in R for researchers who don't use R. So assuming basically zero knowledge whatsoever, and it's a tutorial that takes you through all the basics of data visualization in ggplot. We've got a book on applied data skills. So this is a course that Emily Nordman and I teach to National Health Service workers mostly, it seems, but it's a micro-credential in Scotland that professionals can take for CPD. And there's no stats content, but it walks you through how to create a reproducible report. How do you get data into R? Do you wrangle the data, create tables, create plots, and then generate a report? And we've had also administrative staff take this and said, like, things that they used to do that took 3 months every year to create this report out of the same data they get every year. They've now made a reproducible report and they can just run it in 5 minutes every year. It's like, do not tell your boss that you can do this and just take 3 months off. And then if you want a little bit more kind of research focused content, there's data skills for reproducible research, which goes over a little bit of stats and some data simulation and how we use that. I'm going to talk a little bit more about data simulation soon. And if you want an outstanding course on statistical models that's based on data simulation and using that to help you learn, Dale Barr's Stat Models course is what we teach to level 3 psychology students here, undergrads. But I've gone through the book and I learned so much from it. And there's a bunch of other books. They're all open source. So if you want to use these materials, both for your own learning, but also as a basis for things like if you want to develop textbooks for the students that you teach, they're all open source. Please, please use them. Don't reinvent the wheel. It took us a while to get to this stage and we want to help other people get there faster. And I talked a little bit about online communities. So again, on your skills development journey, there's a bunch of groups and resources that are cool. These are basically mostly R-based, though. Our ladies, I think they're not real picky about your specific gender, but is a very non-men focused group. R for Data Science, again, they are the group that runs Tidy Tuesdays, and they do a bunch of other, I think they run the tables competition as well, and just have a lot of resources for learning R. Coding Club is something that I run out of Glasgow, but it's usually online. So in the fall, every year, we'll do some sort of thing. I think I might run package development again this year. We had it last year and it was pretty fun, I thought. And then I would normally just put R Stats Twitter because like that used to be the best community, the Twitter R Stats people, but I'm no longer a Twitter person. There is an R Stats community on Mastodon. We were talking earlier, like it's not quite the same, but hashtag R Stats on social media, you will probably find some people. Another like a fun thing that you can do to develop your skills is get into art. So Danielle Navarro, it's the most amazing art created in R. You should go see her website on that. There's also a weird subset of R people who are like really making R memes, and it's quite satisfying once you start to get them, and then you can also create them. But just be aware if you are creating textbooks for your undergraduate students, the memes get outdated and they make you seem real old real fast if you put them in your textbook. All right, and then I just need to Raphael Morel, earlier this year, maybe last year, started doing a series of musical tributes to R that are absolutely amazing. I'm not going to play any of them here, but I've tucked them in here and you can play them from here. If you're interested in that, they're all hilarious and amazing and really cool. It's just like the community around R stats is extremely creative and makes me really happy. But we're going to get back to another reason to code that you might not have really thought about, which is data simulation. And it's another thing I'm pretty passionate about. So why would we want to simulate data? I've not put the obvious reason on here of to fraudulently, like, do not fraudulently create data. I'm not encouraging you to fraud. There are so many legitimate reasons, though, to learn how to fake your data. So you can prep analysis scripts for pre-registration. I don't know how common pre-registration is in your area, but if it's not, it should become more common. And so when you're wanting to pre-register an analysis, often people just write down, like, I'm gonna look at the effect of this variable on this, not even variable, sometimes like this concept on that concept, explaining their analysis in pretty broad prose, which leaves a lot of room for interpretation. Like, exactly how are you going to construct those numbers? Are they averages or sums of questions in a questionnaire? How are you going to do exclusions? What are the exact settings you're going to use for a principal components analysis? All of those things are not always immediately obvious from prose, but you have to, if you're creating code to do the analysis, you've explicitly said everything you're going to do there. But it's really, really hard to, in fact, it is impossible to write code of any complexity without being able to run it. So if you don't have data, you can't just write the code to do the analysis unless it's an incredibly simple analysis. So using data simulation, you can create a data set for yourself that's going to have the exact same structure as the data you plan on collecting. And then you can prepare your analysis scripts, which is useful for pre-registration. And once you've prepared them, that means the analysis itself takes minutes after you've collected the data. Additionally, if you can do this, if you can simulate data for that look like what you're expecting to get, and you can write analysis code, you now have all the tools you need to do a power analysis. Even if this is a type of analysis that GPower doesn't know anything about, those are the only two things you need to know to be able to do a power analysis. The only other step is do it 100 times or 1,000 times or 10,000 times. So you need to learn a little bit of code to wrap all that up and repeat it over and over again. And then you just look at, what's the distribution of p-values when you did that 1,000 times. But we can also use data simulation to, sometimes your data are too big to share. It would just be burdensome. Maybe you want to have somebody check your code, but the data set that you have is gigabytes, or it's really confidential. You can't share it. Then it's useful to use data simulation to create a smaller sort of toy data set, or a simulated data set that has similar properties to your real data set, but doesn't have the confidentiality problems, so that other people can see how the code runs, actually run the code for various purposes. So I'm just going through these. Next one is enhancing your understanding of statistical concepts. Like, I did not understand mixed effects models at all until I started simulating data and then analyzing my simulated data and seeing where in the analysis the numbers I used to create the simulated data came out. I was like, oh, that's what that number means. Otherwise, like the random effects table in a mixed effects model just was random gibber numbers to me until data simulation. And even now, whenever I encounter a new concept, I just test my knowledge on it by going to simulate some data and then see if it affects the analysis the way that I thought it was gonna. And then the last one is creating demo data for like teaching in tutorials. It's really useful to have some data that you know exactly how it's gonna behave. All right, so how do we simulate data with code? I'm gonna give you a few things now. I feel like there's things in the chat. I can't see the chat. Okay. I'm not gonna have the chat up, but like unmute yourself and yell at me if there's anything that you want me to check or address. All right, so Data simulation. I said it, I'm really passionate about it. I've written an R package to help people simulate data. There's a bunch of different ways to simulate data and different R packages. The package Faux is basically meant to look at data where you've got summary data in a paper, but no real data to look at. So you've got maybe means and standard deviations and correlations, and you want to try to create data based on those summary stats. There's an online Shiny app. So if you don't code at all, you can go to the Shiny app and set up the factorial design. So setting up within and between subject factors, what are the levels, and it will, once you've got the design set up, you can generate a data set. You can generate as many data sets as you want and download them. It will also give you the code for that you would need for Faux to create that. So this can be a kind of learning tool to how to create the code for the kinds of designs you want. I'm not normally into the point and click interface, but there's a lot of people for whom R seems inaccessible, and this is an easier way to simulate data. But there's also, like, you can also code with Faux. So it's an R package, you can download it, and it lets you simulate data in what I'm hoping is a pretty intuitive way. You can just set up things like you're within subjects factors. We have one factor of version. It's got two levels, V1 and V2. And then we can give them kind of like human readable labels that go on the plots. And then condition, control, and experimental. Then we have a between subject factor age group. They're young and old. And then we can set how many people are in each group. You can set a different number for each group, but if you just give it one number, then every group gets 30 or whatever number you put here. The means, there's a bunch of different ways to do this. And then standard deviations, correlations between within subject factors. And this is a bit more for the plot labels. And you decide whether you want it in wide format, where each column, each repeated measure is in a column, or in long format, where each repeated measure is in a different row and each subject has multiple rows. Then it can give you a table of design parameters, so you can double check that it did what you expected it to do, of each of the groups, correlation matrix down here, the ends and the means, and there's standard deviations falling off the table here. We'll also give you a design plot, so you can double check that you set it up the way you expected. So this is a plot of the mean and standard deviation of the population. So the parameters that you input into the design. And then there's also data plots. So it's a violin plot of distribution of the actual simulated data. So this one will differ every time you run a separate simulation. Now, once you've got your design set up in this way, it's really easy to repeat it. You just add a line here, rep, how many do you want? So we can make 100 data sets that are set up like this. And then your next step, if you're wanting to do something like you want to analyze each one of those 100 data sets and do a power calculation, all you need to do is set up an analysis function. Here, this is the code. Don't worry about understanding the code. I'm just telling you it's the code to do an ANOVA on these data, and then a little bit of code that fixes the fact that the p-value column is called PR open parentheses greater than sign capital F end parentheses. It's just a ridiculous column name. We've just renamed it to P so that we can use it later without having to type this constantly. So, but basically what you do is you put your analysis code however you want to analyze your data in any way whatsoever in here. And then what that analysis code outputs is a table that looks like your standard ANOVA table: degrees of freedom, mean squared error, F values, P values. And then this code is the same for every time you would ever want to do this with any analysis in any data sets. You set up your data, you set up your analysis function, and then you run this code on it, and it will give you the power for everything that's in your table. So let's say that the simulation method of power, I feel so powerful in that I review a lot of papers where people are doing something like a mixed effects model, but then they're reporting a power calculation from G-power, which I know doesn't know anything about mixed effects. And I don't really understand what people are doing with G-power sometimes when they're like reporting values that can't have any possible connection to their own analysis. But I think people are doing kind of the best that they can because they don't know any other way to generate power calculations. I'm going to not go on my tangent about why we don't need to do power calculations all the time, but there's an excellent paper by Daniel Lockins about the different ways you can justify your sample size. Power calculation is not the only way, and it's often not the best way. And if you get frustrated by requirements to do power analyses like for grants and stuff, I recommend you read that paper. But yeah, if you want to learn more about data simulation, because there's just a lot to learn, SciPag Simulation Summer School, this is a clickable link, takes you to their page. So the SciPag, or they're UK postgraduate psychologists. They put on a summer school, like 8 or 9 different researchers who do different types of simulations, all gave talks. So I gave one of them about Faux, and they're all on YouTube now. And then the data simulation workshops, I run those. There's tutorials there on how you use Faux, but also how you do mixed effects, how you simulate data for mixed effects models. Right. And I think it's the last bit I wanted to talk about, though, is like now that once you've learned to code and you're doing your analyses using code, it's still not going to solve every single problem. We also need code review. So very recently, Sophia Cruel and some colleagues tried to reproduce the results of all 14 empirical articles in an issue of PsychScience. So they all provide at least some data. 6 of those articles provided code. And they found that only one of the articles was exactly reproducible, that they could create all the stats that were in the paper from well, this one had code. 3 of them, 2 that didn't have code and 1 that did, were essentially reproducible. Like maybe there was a rounding error or something. But a bunch of the articles had data access problems, so they didn't share all the data that was needed to actually reproduce all of the results. Or the data were meant to be somewhere, but they actually weren't where they were linked. All of these things can be addressed with code check. Now, I have an undergraduate student, so a level 4 psychology undergraduate, who proposed this project before Sophia's paper was out, and I didn't know anything about Sophia's paper. But it's done basically the same thing, but with all of the articles in the entire year. So all of 2022 in PsychScience. So he looked, there were 142 articles, and 104 of them had an open data badge. Now, the open data badge at PsychScience specifies that to get an open data badge, you need to have your data open, but you also need to include all the code required to produce all of the results that are reported in your paper. So an open data badge is actually an open data and code badge at PsychScience, although I polled people on Mastodon about this and they don't believe that. But it's technically there in the write-up. But when I looked at all 104 of those papers, 3 of them had corrupted downloads. Like you went to OSF and tried to download it, and all you got was something that would, like a zip file that wouldn't open. And we couldn't figure out how to fix those. There were 14 where the code wasn't accessible. They didn't share any code. And there were 13 where the data weren't actually accessible. They said they shared data. They got a badge for it. But when you went to the website, it was data available upon request, or it was the data are embargoed until a later date, or there was just nothing there. There were 74 papers that had open data and open code that could be downloaded. 17 of them didn't use R, and I didn't expect an undergrad to like teach himself Python just for this project. So he only looked at the 57 that had R, RMD scripts and data. He tried to run all of those, set a 10-minute timer so that otherwise he would probably still be working on it. Could successfully run 28 of the scripts, although I think only one of those could he run without any modification. The other 27, he had to go in and fix some errors that people had made with things like absolute paths, or they changed the names of the data files so that the data files that they uploaded to share didn't have the same name as the code that they used to analyze them, and had to go like figure out what's wrong with that and fix that. Or other things like packages that weren't accessible on CRAN. So they've used packages that are that you'd have to Google to figure out where they are and how to install them. And there wasn't any information in the actual script to tell you how to do that. But 28 of them ran. He didn't check if they got reproducible results or anything, but they ran from beginning to end at least. That was the goal of this project. 28 of them he could not figure out within 10 minutes how to get them to run. And one of them did run, but it didn't finish running within 10 minutes because it had a very long analysis that was not his fault that it was a long analysis. It looks like it would have run if he'd had enough time. So all of this really highlights the fact that even if we have code and we're sharing our data and we're sharing our code, it might not be enough. You're going to need to do some basic checks. And I think that there are some like really basic checks that could have fixed most of the problems that he saw in this code. And that you can just do with basic levels of code review. I'm working on a book right now of how to do code review. And this is a little overview of that. The goals of code review. Number one, figure out, does it run? Like if you just send your code and your data, or the link that you're going to put in your paper, send that link to a friend and say, can you download this? Can you run it? If you can't, tell me what error messages you got. Just that very basic level of code check probably could have fixed almost everything that went wrong in that student's paper. But if you want to go beyond that, you could say, like, here's my paper. Here are all the numbers that I'm reporting in the paper. When you run the code, do you get the same numbers? Trying to make that as easy as possible for the person who's doing code check for you to check. A level beyond that is it auditable and understandable? That is, have you organized your code in such a way that if I'm reading through your paper and I say, okay, yeah, analysis 4, I want to go see a little bit more of the code of that. Can I find it in your code, or do I have to read down 1,000 lines of uncommented stuff and guess that this is probably the one that corresponds to this bit of your paper? So that's what I mean by auditable or understandable. And then beyond that, there are some best practices that I'll talk about in a second. And the kind of highest level of code review is what you're doing actually correct and appropriate? Now, code review isn't helping somebody debug their buggy code, or giving them help on how to write code that they don't know how to write. Or giving them statistical help. So if I agreed to do code review for somebody, I make sure to tell them up front, like, I'm not writing code for you. And if your stats are inappropriate for your data set, I'm not judging that unless I've agreed to do that as well. But I feel like that's a separate thing. There's a Riot Science talk that I gave recently, and that's on YouTube, where I go into some of these key concepts for things like best practices in project organization, how you name things, how do you make it easy for somebody to use your code? Because if we're going to be sharing our code, that's kind of the ultimate goal of writing the code, is you're going to share it with somebody. Oftentimes that somebody is future you, and future you does not remember anything really. So like, assume that future you has some real bad amnesia, and write your code to make sure that they're going to be able to understand it without being able to talk to past you. Right, and then sorry, the book is going to have like coder checklists, How do you make sure that you set up your code in a way that makes it easy for other people to review? And some reviewer checklists. So if you get code to review from somebody, or you're reviewing a paper for a journal, if you're reviewing a paper for a journal and the person has supplied open data and open code, it would probably make them happy if you had a basic check of it. There are so many times that I've submitted papers with data and code, and I can see how many people have downloaded things on OSF. And I know for a fact that nobody has ever downloaded it during the review process. Nobody's ever looked at the code. They don't talk about it, which is really frustrating. So having that skill set as a reviewer is also really useful. All right, so that's my code review rant over. And yeah, so the links on here are to this talk, but also the code for creating every little bit of this talk. And I'm happy to answer any questions about it. Thanks.
Thanks so much, Lisa. That was great. And there are no questions so far in the chat. I think mostly people are expressing gratitude at you making your psyTeachR available to everybody, because we don't really have anything like that in sports and exercise science or kinesiology at the moment. So I think we lean a lot on psychology for some of those types of tutorials, but hopefully coming soon.
We are thinking about trying to set up a kind of affiliate program for psyTeachR, so which would not necessarily have to be psychologists, but we're stuck with the name. But yeah, like we'd love to help other people figure out how to do these sorts of things, how to create resources for their area.
Yeah, that would be really cool, because I'm pretty new to R myself, and I find that a lot of the examples are not obviously based in my field, and sometimes the analysis is slightly different. So you're trying to kind of make the jumps yourself, and it would be nice to have a resource that you could go to like yours, where everything is in the one spot all together. Okay, guys, so if anybody has any questions, feel free to either put up your hand or just unmute yourself. I think I'll just kick off the questions at the start, and just thought that paper, or that analysis by your undergrad was really, really interesting, and the kind of numbers are a little bit scary there in not being able to successfully run scripts. But it's something I've thought about quite a bit, and as I said, I would still consider myself a newbie to R, but what is the kind of, I suppose, going forward with packages for R and the different versions for reproducibility? It's very hard thinking, for example, that I've put up, I've used a certain package, a certain version number for this analysis for one of my papers, but is that version going to be still alive, or is there something I should do in my code to say, like, should I literally say I'm using version number X for this in the code of the manuscript, or what would you recommend for that?
All right, yeah, this is a huge problem. And there are a bunch of solutions. I think for RENV, RENV is probably the go-to solution right now, which downloads, or it keeps a version of the packages that you're using in with your project, so that anybody who downloads that can use exactly the versions that you're using. Now, depending on what you're doing, there can be some interactions with your operating system, in which case the more secure version, but slightly harder to set up, is containers. So things like Docker, you can containerize. Basically, you've got your operating system, your version of R, all of your R packages, it's all inside one bundle, and you can put that on the web, and people can interact with your data through a web interface, or they can download the bundle, and then that container is on their computer, and then they can interact with it in the exact same environment that you did the analysis. That is sort of guaranteed to work as long as you can open containers. Like, nothing's guaranteed to work forever in computer science. But right now, yeah, if you're very worried containerizing, but that takes a little bit of expertise and can be frustrating. I get it to work 90% of the time now, but that 10% of the time when it doesn't work, what it's doing right now is filling up my entire hard drive. And it's trying to put my entire hard drive in the container, which is not a thing that can happen. So when it doesn't work, it's really frustrating. So I tend not to mention it in intro to coding. But RENV, is generally pretty user-friendly, and their help for how do you get set up. Like, it's another thing. When it goes well, it's really simple, kind of just 2 lines of code to get it set up and it works fine. And when it gets buggy, it's real hard to fix.
Yeah. You know, that's a good resource. James just sent the link into the chat there, because I think sometimes when, especially again with me, when I'm new to coding and everything like that, but then I'm kind of harping on about reproducibility and replicability, you feel like you hold yourself to a slightly higher standard. And
But
you know,
the dead simplest one is session info. There's a function in R called session info, and it will pop out all of the package version numbers that you're using right now, and like the operating system, the relevant stuff. It's a bunch of text. Save that, and that's at least a record of what happened. And then somebody can attempt to reconstruct on that operating system that version of R, those package versions. They might not be able to find the package versions, etc. So it's not totally foolproof, but it's, that's your first step. It's enough to be going on with, just to record all of those. And there's just one function that will help you do that.
yeah, that's a really good idea.
But yes, no, we've got some expert coders in the room, and please do jump in if you want.
Can I ask a question? I'm not an expert coding at all. So first, thanks, Lisa, for your nice presentation. I've been recently required to share an R script for a paper I submitted to the European Journal of Applied Physiology. When I was, because I'm not an expert, it was my first time, producing that kind of document. I was just looking for other papers in similar journals that would, serve as an example for me to follow, right? And on my search, I realized that there weren't many papers with R code shared in the field of exercise physiology or applied exercise physiology. So my question to you is, how can we make this code sharing more common in areas where this is not really a mandatory part of the submission process? What's your experience in psychology? How this trend actually started?
I'm trying to think of what is the history of this sort of the open science movement and the idea of open data, open code badges. Part of that was getting journal editors on board. So there's been journal editors like Stephen Lindsay at Psych Science who are just really enthusiastic about this and making it become policy. So I sit on the American Psychological Association Open Science and Methods expert group. We're not allowed to be called a committee for esoteric administrative reasons. But we make recommendations to all the editors at all the 100 APA journals and around open science. So trying to get people who are enthusiastic about that onto these sorts of committees in these positions to make these decisions, and lobbying the big journals in your area to say, this is why we need open code, open data. Are there ways to not necessarily make it mandatory, but to encourage it? And there are also ways, often you'll hear people talk about, I can't have open data, and kind of open code is really hard to deal with if you don't have the data as well. So when you're talking about open code, there's often the reasons people say they can't share their code is because they can't share their data. Number one, data simulation. There are ways to be able to share something that makes your code run so people can check your code, even if you can't really share your data. But there are also ways to share data. No, be quiet, watch. And so they're managed archives. So if you're in the UK Data Service will manage data for you, making sure that only people with the appropriate qualifications and under the appropriate licenses can have access to more sensitive data. So thinking about how does that work in your area, what are the managed archives, and making sure that people know about it. But also, like, grassroots, just start sharing your code, even if it's not required, and and talk to people about why it's useful.
Early on, STORK had some conversations with some of the bigger journals in the in our field. I remember, I can't remember what year it was, maybe 2019. At ACSM, we managed to have a meeting with Bruce Gladden, who was the editor-in-chief of MSSC at the time. And it was kind of, we've still got a very sort of like old guard series of people, set of people who are kind of in charge at the various journals, but there are certain people in certain positions that are kind of strategically placed and have bought into a lot of this stuff. So take like someone like Grant Abt at Journal of Sports Sciences, who is very heavily sort of promoting more open science practices and things like that. But even he sort of faces barriers with the rest of the editorial board to try and make things policy. I was just going to pop a link into the chat. I mean, I would encourage everyone to sign up for this if you're not aware of it, but something I've signed up to is the Peer Reviewers Openness Initiative. And so now whenever I receive review requests, I won't agree to review anything that I'm not able to review fully in terms of data, code, materials, etc., unless there's a very good reason why they're not able to share those things with me. So for one thing, it really cuts down on your peer review load. So that's quite nice. But it's kind of those little behaviors that start to, if authors are submitting work and going, oh crap, a reviewer might ask me to share my data or share my code or whatever again, then maybe it will slowly start to filter out and change behavior.
So hard to find reviewers lately that, like, I think editors are becoming more willing to ask for those sorts of things just because they don't want to have to ask another 28 reviewers to find somebody. But yeah, no, the Peer Reviewers Openness Initiative is great. What was the thing here? No, grant agencies are starting to become more aware of open science and mandating sharing data in their own internal repositories. If they're going to fund your work, they ought to have access to all the data. So making that sort of argument in different places, if you need to make arguments for why does my department need to invest in continuing professional development to teach people this, it's because the funders are going to start requiring it. Journals are going to start requiring it. You'd better learn the skills to do it.
I think when I was starting to learn how to code as well, and I'd be interested to hear your thoughts on this, was, obviously coding is overwhelming. There's so much to learn and everything like that, but I would say particularly in R, there's so many different packages for the same thing. So can be a little bit overwhelming. And then I find that certain packages work better with other packages because you've set up your data a certain way or anything like that. Is there any kind of resources or anything online about like that kind of shows you which packages are nicer to use together? Just would say for beginner coders where it is a little bit difficult in deciding that, or have you kind of thought of anything like that before?
So we're often really focused on the ideas of analysis because when you're talking about statistical software like SPSS, it's really mainly just analysis. The main thing that I do in R is data wrangling, like putting data sets together, reshaping them. The analysis part itself is actually pretty straightforward and only generally a few lines of code. That's where you need sort of expertise within your area to know what are the right packages, exactly how do they work, how are the different options different from each other. We had a presentation on k-means cluster analysis today in our methods and meta-science group, and learned about like the 3 different algorithms that are used to do clustering and like the 18 different other non-k-means clustering types of things that you could do to cluster data. And it seems to be kind of arbitrary if each area picks their favorite way to do cluster analysis. So you're going to need kind of a community of people who are coding and doing similar kinds of things to understand what's going on together. But like with data wrangling itself, I'm a big proponent of tidyverse. I love tidyverse. It goes together with so ggplot for creating plots, readr for reading in data, dplyr, and what's the other one? tidyr for kind of your reshaping and merging data. And then there's Forecats that helps you deal with factors, and they all go together. And you can load them all like together as one thing with the tidyverse library, or library tidyverse. That all goes together pretty well, but then it's basically you needing to learn how to think about data and how to reshape data like from wide to long and back again, in order to get it in the shape it needs to be for every particular analysis. I'm not sure if that answered your question, but yeah, but disciplinary communities are probably the answer.
I feel like tidy data kind of fits nicely in the whole everything is a linear model sort of framework as well, because
Yes.
so many things just want things in long format, and it's just like I hate seeing that big wide format nowadays.
Yeah.
And but we don't get taught. I mean, I guess most fields don't get taught. I mean, well, I try to now teach my students that everything is like they don't find out until later when the curtains get drawn down. It's like, oh my god, t-test.
Yeah,
it was t-test all along.
Yeah, but it's one of the many mistakes I've made in the faux package that it defaults to wide format and you have to put long equals true to get the data in long format. But like once you start package development, if you make mistakes like that, you can't change them because you're going to break people's old code. So don't start developing packages too early in your career. Wait until you understand what's going on.
Advice taken on that one. Okay, if anyone else has any final questions, please don't hold your silence now. Otherwise, Lisa, thanks so much. It was a fantastic talk, and thanks a million for coming on and speaking to us. I have that link for the slides anyway, so I will share that, guys, on our Twitter page, and I'll link it in kind of with the YouTube recording of this talk as well.
Okay. Thanks so much for having me.
See you soon. Thank you.
Mm-hmm.